Welcome back to the show, everyone. Today, we're diving deep into the world of large scale model training with a groundbreaking paper from Meta AI titled PyTorch FSDP Experiences on Scaling Fully Sharded Data Parallel. To help us understand this work, we have two incredible guests: lead researcher's name, the lead researcher on this project, and field expert's name, a leading expert in the field of distributed deep learning. Let's get started.
Thanks for having me. I'm excited to talk about FSDP and how it's revolutionizing the way we train large models.
It's a pleasure to be here. This paper is certainly making waves in the community. Before we dive into the specifics of FSDP, can you give us some background on the challenges faced in training these massive models? Why is there a need for new solutions like FSDP?
Absolutely. The field of deep learning has exploded in recent years, with models growing larger and more complex than ever before. Think about GPT-3, which has 175 billion parameters, or even larger recommendation models reaching over 1 trillion parameters. These models are incredibly powerful, but training them presents a unique set of challenges. One of the biggest challenges is memory capacity. These models simply don't fit on a single GPU device. Existing methods like distributed data parallel, DDP, and PyTorch rely on replicating the entire model on each device, which quickly becomes infeasible for these massive models.
So, how does FSDP address this issue? What makes it different from previous approaches?
FSDP tackles this memory problem by introducing the concept of sharding. Instead of replicating the entire model, FSDP breaks down the model into smaller units and shards the parameters within each unit across multiple devices. This allows us to distribute the memory footprint across the entire cluster, making it possible to train models that were previously out of reach.
This sounds like a clever approach, but how does it ensure that all the devices are working together correctly and maintaining model consistency?
That's where FSDP's communication optimizations come in. The system leverages a combination of techniques like communication overlapping, prefetching, and gradient accumulation to minimize communication latency and maximize GPU utilization. This ensures that all the devices are working together effectively and efficiently to train the model.
Can you elaborate on these communication optimizations? This is where things get really interesting for someone who's trying to understand how the technology actually works.
Sure. One key technique is overlapping communication with computation. Instead of waiting for a communication operation to finish before starting the next computation, FSDP uses separate CUDA streams to run communication operations asynchronously. This allows communication to happen concurrently with computation, reducing idle time and improving overall efficiency.
And prefetching. How does that factor into the optimization process?
Prefetching allows FSDP to anticipate the next set of parameters needed for computation. It issues the all-gather operation, which retrieves sharded parameters from other devices, before the reduce scatter operation, which reduces gradients across devices for the current batch. This minimizes the time spent waiting for data, improving the overall training pipeline.
This all sounds great, but what about the impact on the overall memory usage? Is it possible to reduce memory consumption without compromising performance?
That's where the rate limiter comes in. FSDP uses this feature to control the memory impact of the CUDA caching allocator, a mechanism that manages GPU memory. By limiting the rate of communication operations, FSDP prevents the CPU thread from aggressively allocating memory blocks, which can lead to fragmentation and slow down training. This helps ensure that memory is used efficiently without compromising performance.
Okay, this is getting complex. So how do you actually use FSDP? How is it implemented in PyTorch?
FSDP is designed to be user-friendly and non-intrusive. It provides two main APIs, the fully sharded data parallel model wrapper and the fully shard module annotator. The wrapper allows you to wrap your entire model with FSDP, while the annotator allows you to apply FSDP logic to specific modules within your model, preserving the structure and parameter names. This flexibility allows users to integrate FSDP into their existing workflows without major changes.
So, from your perspective, what are the key innovations that FSDP brings to the table? How does it compare to existing approaches in the field? FSDP represents a significant leap forward in large-scale model training. Its deep integration with PyTorch's core components sets it apart from previous solutions. Unlike techniques like zero or cross-replica sharding, which often rely on modifying the framework internals, FSDP offers a more robust and maintainable approach. Furthermore, FSDP's flexibility in choosing sharding strategies allows for fine-grained control over the memory throughput trade-off, which is crucial for optimizing performance on diverse hardware configurations. Let's talk about the experiments you conducted. Can you give us a breakdown of the experimental setup and the key results you achieved?
We evaluated FSDP on a variety of models, including popular language models like T5 and MinGPT, as well as a large recommendation system model called DHEN. These models ranged in size from 611 mem to 175 B parameters. Our experiments were conducted on a cluster of 80 gig A100 GPUs interconnected by a high-speed ROCE network. The results were incredibly promising. We found that FSDP achieved similar performance to DDP on smaller models but scaled to significantly larger models that exceeded the memory capacity of a single GPU, where DDP failed. In fact, we were able to train the 175B MinGPT model with FSDP, achieving over 173 and 186 Tflops per GPU with batch sizes of 1 and 2, respectively. This demonstrates FSDP's ability to handle large models with expensive computations and high-speed network interconnections.
These are impressive results. What are the broader implications of these findings? How do they impact the field of large-scale model training?
FSDP opens up new possibilities for research and development in various domains. It empowers researchers and practitioners to train larger and more complex models, pushing the boundaries of what is achievable. This could lead to breakthroughs in natural language processing, computer vision, drug discovery, and other fields. It's also important to note that FSDP is designed to be user-friendly and accessible. This will likely lead to its widespread adoption, democratizing the training of large models beyond a select group of experts. This will accelerate innovation and drive progress across the field.
That's a very interesting point. Do you have any thoughts on the potential applications of FSDP? What are some specific areas where it could have a significant impact? FSDP has the potential to revolutionize the development of large models across various applications. For example, in natural language processing, FSDP can be used to train state-of-the-art language models for tasks like text generation, translation, and question answering. In computer vision, it can enable the development of advanced models for object detection, image segmentation, and video analysis. FSDP can also be leveraged to build more personalized and effective recommendation systems for e-commerce and content delivery. Beyond these specific applications, FSDP could also have a profound impact on scientific research. We could see the development of AI-powered tools and simulations for tackling complex challenges in physics, biology, and chemistry. This could lead to breakthroughs in fields like drug discovery and climate modeling. It's truly exciting to see the potential of FSDP. But like any technology, it's not without limitations. Can you shed some light on the challenges and limitations that still need to be addressed?
Yes, there are a few areas where we're still working on improvements. One challenge is ensuring mathematical equivalence between training with FSDP and local training. While FSDP is designed to achieve this, certain optimizer computations that depend on unsharded parameters or global states can be problematic. This requires careful consideration when selecting optimizers and might necessitate further research on co-designing optimizers with sharding. Another area we're actively working on is handling shared parameters effectively. Ensuring that shared parameters are not flattened into multiple units and are unsharded correctly for all usages can be complex. This requires careful attention and could benefit from more robust and automated solutions.
Those are definitely important considerations. Where do you see FSDP going in the future? What are some potential research directions that could further enhance its capabilities? There are several exciting research directions for FSDP. One area of focus could be developing adaptive and dynamic sharding strategies that adjust based on real-time performance feedback. This would optimize resource utilization and communication efficiency during training. Additionally, exploring new communication primitives and optimization techniques specifically tailored for large scale models and diverse hardware architectures would be crucial for achieving even higher training throughput and scalability. Another promising direction is combining FSDP with other parallelism paradigms, like pipeline and tensor parallelism. This could enable even more efficient training of even larger models. As we push the boundaries of model size and complexity, it's essential to have a toolbox of techniques that work together seamlessly. It sounds like the future of large scale model training is bright. Before we wrap up, can you leave us with your final thoughts on the significance of FSDP and its role in the future of deep learning?
FSDP is a critical step towards democratizing the training of large models. By providing a user-friendly, efficient, and scalable solution, it empowers researchers and practitioners to tackle increasingly complex problems. Its deep integration with PyTorch ensures that it remains a robust and reliable tool for future advancements in the field. As we continue to push the boundaries of what is possible with deep learning, FSDP will undoubtedly play a key role in driving innovation and shaping the future of AI.
That's a powerful conclusion. We've learned a lot about FSDP today, and I'm confident that listeners will be eager to explore this exciting technology further. Thank you both for sharing your insights and expertise. This has been a truly enlightening conversation.
It was a pleasure to be here. I hope our discussion provided valuable insights for everyone.
My pleasure. I'm excited to see how FSDP continues to evolve and shape the future of deep learning. And that concludes our show for today. We hope you enjoyed learning about the incredible advancements in large-scale model training with PyTorch FSDP. Be sure to check out the links in the show notes for more information and to stay updated on the latest developments in this exciting field. Until next time, happy learning.